In this video, we are going to do another, well, not heating curve, but cooling curve problem. We're going to work through problem 16 here. So let's look at problem 16. How much heat is evolved? Evolved is a fancy term for release when you convert 1 mole of steam at 145 to ice at 50. All right, so what we want to do is we want to draw our cooling curve for this problem. So temp on the y-axis, heat on the x. So we start at 145 as a gas, and we're going to lose temperature until we hit the boiling point or condensation point, which is 100. We're going to condense. So we're going to go gas to a liquid. After we're done condensing, we're going to cool off until we hit the crystallization or freezing point. For water, that's 0. So this is all liquid. All right. Then we're going from liquid to solid. So we're going to stay at 0 during that process. And then we're going to go down to double check. It's minus 50. Yep, it's minus 50. So like in the previous video I posted, we have 5 segments and we have 2 equations again. If you're not sure what these equations mean, please look at my previous video on our heating curve where I explain them again. All right, so let's solve this segment by segment. So segment 1, we are cooling, so we're changing temperature. So Q equals mass. Well, we have 1 mole of water. So we have 1 mole of water. The molecular weight of water says that for every 1 mole of water we have, that's 18.02 grams. So we actually have 18.02 grams of water, since it's 1 mole, times the specific heat capacity. So we're at a gas. The heat capacity of steam is 2.01. So multiply by 2.01. Let me have my units. So that's grams. That's joules divided by grams centigrade. Then multiply by delta T. Our final is 100. Our initial was 145. That's negative 45. And so let me do this calculations really quick here. So that is negative 1630 joules or negative 1.630 kilojoules. That's segment 1. Segment 2, we're doing a phase change, so we want to use our phase change equation. Q equals N, which is moles, so we have 1 times delta H. So we're doing condensation here. However, in the problem, I only give you vaporization. Remember, vaporization and condensation are opposite processes, so their delta H's are the same value, just opposite signs. So delta H of vaporization is negative 40.7 kilojoules per mole. That was 1 mole. So the energy it takes to cool 1 mole of steam to water is negative 40.7 kilojoules. Right, segment 3. Now we're water. We're going to cool down to the crystallization point. So Q equals mass, 18.02, multiplied by the specific heat of water, which is 4.184 joules grams Celsius or centigrade. Then we're going to multiply that by our final temperature 0. Our initial was 100. That's negative 100. So 18.02 times 4.184 times negative 100 is 7,000, negative 7,540. I'm rounding, by the way, 39.5. Or negative 7.540 kilojoules. So now our liquid is at 0 degrees, so it can start to turn to ice. So Q equals 1 mole, and now we need delta H crystallization. Here, I give you delta H fusion, but it's the same idea. Delta H fusion is equal to negative delta H crystallization. So delta H crystallization is negative 6.02 kilojoules per mole, which is negative 6.02 kilojoules. So that's how much energy it takes to freeze 1 mole of water, or how much energy is released, I should say. And then lastly, we are taking our ice down to minus 50. So Q equals the mass, 18.02, times the heat capacity of ice, which is 2.09 joules gram Celsius. Our weight was in grams, multiplied by our change in temperature. Our final temperature is minus 50. Our initial is 0. So 18.02 times 2.09 times negative 50 is negative 1.883 joules, or negative 1.883 kilojoules. So we calculated each segment what the energy is. Now what I need to do is just add up all the segments, because I want to know the energy of this total process. So that's what I'm doing right now, is I am adding up the energies from every single process. And the amount of energy that was released was negative 57.77 kilojoules of heat. Now, one thing I want you to notice, when we did our problem in the previous video, all the energies were positive when we were heating. When we're doing the problem in this video where we're cooling, all the energies were negative. And that's how it's going to work. If you are cooling, you're always releasing energy. They should always be negative. If you're heating, you're always adding energy. It should be positive. So if you ever come in a situation where you have both positive and negative values, most likely you messed up one of your delta H's. You forgot to switch it. But yeah, that is all for this video. If you have questions, feel free to let me know. Otherwise, I will see you later.